If you didn't have the second restriction, the notion of the extension would be trivial, because if you have universal equal goodness, everything gets an extension. Would be an extension of everything. Right, standard properties, the one we all know is transitivity, and it basically says if you take any three alternatives x, y, and z, if it is the case that the pair xy is in R and the pair yz and the pair yz is in R, then the pair xz should be in R. This one, very standard. Transitivity is a nice property, very well behaved. In particular, for the purposes of this talk, it does have a well-defined closure operator, the transitive closure. And the transitive closure of any relation R is defined by looking all possible chains of at least as goodness relations. If you can find a chain from an alternative to another, then this first alternative and the last in the chain also are included in this relation. So that's the set of all pairs x and xy, such that you can find a positive integer k and k plus 1 alternatives, x naught to xk x, such that we start out with the x. X is the first element in our chain, and then we make our way all the way to y. That is x k minus 1 xk is in R for all k. And at the end of the day, at capital K, you arrive at y. All very well known and very well established, and indeed we can verify that this possesses all the properties of a closure operator. In particular, it clearly is a superset of R, TC of R, a superset of R. The relation R is transitive if and only if the relation is equal to its transitive closure. Furthermore, the transitive closure has a minimality property in the sense that it is the smallest transitive relation that contains R, and finally, it is the transitive closure is monotonic with respect to C. Again, totally well behaved. The only reason why some transitivity might not be the best way to go on under some circumstances is that it is quite demanding, and I'll come back to that very shortly, now in fact. So the weakening proposed by Godreau is what we now call Suzumura consistency. Again, I should mention, I came up with this label. The reason is, in all the years I worked with Godreau, he would be too modest to call anything after himself. And what happened was that at some point I wrote a paper by myself, which was a bit of a survey paper. And the one primary motivation for this was because the term consistency is so general, and there's so many consistency conditions in the literature that have nothing to do with that I thought we have to distinguish it somehow. Once I've done that by myself, to find this. But again, this was yet another indicator of his humility, right? He wouldn't want to have something named after him, even though he was the designer. All right, so what Suzumura consistency does is it weakens transitivity and strengthens acyclicity by ruling out cycles with at least one instance of patterners, right? Acyclicity rules out patternless cycles, where all instances are instances of patterners, but Suzumura consistency is stronger. Even if there is only one instance of patterners, we don't want to have this. So basically, what this says is, if you have any two alternatives, x and y, if the pair xy is in the transitive closure of R, then that better not be the case that yx is in the asymmetric part of 1, right? If you had y is better than x, you'd have a cycle. Some instances are equal goodness or betterness, and at least there is one instance of betterness, and that clearly leads to trouble. Now, in comparison to transitivity, that's clearly weaker, except if the relation R is reflexive and complete to begin with. Then the two of them are equivalent. Otherwise, transitivity is strictly stronger than Suzumura consistency. And the reason why I think Suzumura consistency makes a lot of sense is that if we're in an environment where we don't have completeness, we already allow for the fact that some alternatives may not be comparable. To demand that if we have a chain, the same going from X to Z like this, demanding that X has to be at least as good as Z is much stronger than we really need. All we want is rule out unpleasantness. And unpleasantness would be to have a cycle where we declare Z to be better than X. Again, if the relation is complete and reflexive to begin with, there's no difference between the two. But if it is incomplete, so more consistency seems to be the more modest requirement. And as I already mentioned, it turns out to be necessary and sufficient for the existence of an ordering extension. It is in essence exactly what you need to avoid a money pump, right? You cannot, if Suzumura consistency is satisfied, it is not possible to milk an agent by basically going through a sequence of trades, and at the end of the day, the agent is willing to pay a positive amount to get back the alternative he or she started. And again, most relevant for today's talk, Suzumura consistency does have a well-defined closure operator. Here it is. So there is such a thing as Suzumura consistent closure. It is defined as follows. First of all, is that you have the relation R itself. You don't have to do this explicitly here because it's included for the case K equals 1. In this case, it's not automatically included, and you will see why in a moment. But you have to add to that is all pairs XY, such that XY is in the transitive closure of R, and YX is in R. If you have such a situation, you definitely have to make sure that XY is in this relation, because if not, this relation is a strict relation and we have a cycle. It turns out the other way around. If you do this for all possible pairs, that's enough. And indeed, this closure is this relation is a well-defined closure operator. It possesses all the relevant properties. Now, if we move on to quasi-transitivity. Quasi-transitivity, as we know, is very easy to define. It just says that not the whole of R, but only its asymmetric part is transitive. And in this case, can everybody read this, or is it a bit of a problem because of the dates here? Okay, in this case, there is no such thing as a closure operator. You can see this with a very simple example. Suppose, for example, we have a relation that consists of the two pairs XY, YZ. Right, that's it. Notice that these are also in the asymmetric part of this relation. Now, if you add the pair XZ, you come up with a quasi-transitive relation, but you can come up with a quasi-transitive relation also by adding YX. You turn this betterness into equal goodness, or you can turn this betterness into equal goodness, and again, all of these are quasi-transitive. So there is no unique way of coming up with a superset of R that generates quasi-transitivity in a unique way. And notice again, here's my initial naive error. Of course, all of these relations are Suzumura consistent, so Suzumura consistency does not fail. So what do we do instead? Well, again, we go for the consolation prize. And what we ended up with is we have what we call a minimal quasi-transitive extension. Okay, now question, shall I erase and continue here, or shall I continue in these chords where you have to crane your necks? So it's up to you. No, seriously, if everybody's okay with these definitions, I'm happy to erase them. Everybody all right?
I have just a curiosity about the definition of extension.
Mm-hmm.
So if I break some indifferences, that is an extension. Because R is like, because right, the first part is
Exactly.
wrong.
Yeah,
The first part. Right.
So good if I erase it. Again, if you don't remember something, just